Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine ABCD constants of a three-phase medium length transmission line based on its nominal pi equivalent circuit. We shall also learn how to calculate percentage voltage regulation and efficiency of transmission of this line using those constants. Neglecting ligands and using nominal pi method, we have to determine the sending end voltage, the efficiency of transmission, and the percentage voltage regulation of a three-phase 50 Hz 130 km long overhead transmission line delivering 24 megavolt ampere at a power factor of 0.8 lagging to a balanced load at 66 kV. Each conductor has resistance of 0.109 ohm per kilometer, inductance of 1.2 millihenry per kilometer, and capacitance of 0.00967 microfarad per kilometer. Let us first write down the given data. Load SL equals to 24 megavolt ampere, that is equal to 24 into 10 to the power 6 volt ampere. Line to line receiving end voltage VR line equals to 66 kilovolts, that is equal to 66,000 volts. For star connected system receiving end voltage per phase, VR equals to VR line divided by root 3, that is equal to 66,000 divided by root 3, that gives us 38,105 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for load SL equals to root 3 times VR line into IL. Therefore, load current IL equals to SL divided by root 3 times VR line. Using values we get 24 into 10 to the power 6 divided by root 3 into 66,000. That gives us 210 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 210 ampere at an angle minus 36.8699 degree. Here, load current IL equals to receiving end current IR. Power delivered to the load PL equals to SL into cos phi L. Using values we get 24 into 0.8, that is equal to 19.2 megawatt. Given length of the transmission line D equals to 130 kilometers, resistance per kilometer per phase R1 equals to 0.109 ohm, inductance per kilometer per phase L1 equals to 1.2 millihenry, and capacitance per kilometer per phase C1 equals to 0.00967 microfarad. Let us now calculate resistance per phase. R equals to R1 into D. Using values we get 0.109 into 130, that gives us 14.17 ohm. Inductance per phase L equals to L1 into D. Using values we get 1.2 into 130, that is equal to 156 millihenry or 0.156 Henry, and capacitance per phase C equals to C1 into D. Using values we get 0.00967 into 130, that is equal to 1.2571 microfarad, or 1.2571 into 10 to the power minus 6 farad. Now we shall compute inductive reactance per phase. XL equals to 2 pi f into L. Given supply frequency f equals to 50 Hz. Therefore, XL equals to 2 pi into 50 into 0.156. That gives us 49 ohm. And capacitive susceptance per phase BC equals to 2 pi f into C. Using values we get 2 pi into 50 into 1.2571 into 10 to the power minus 6. That gives us 395 into 10 to the power minus 6 mho. Let us now determine series impedance per phase of the transmission line. Z equals to R plus JXL, that is equal to 14.17 plus J times 49 ohm. This may be written in polar form as 51 ohm at an angle 73.87 degree, and shunt admittance per phase Y equals to J times BC, that is equal to 0 plus J times 395 into 10 to the power minus 6 mho. This may be written in polar form as 395 into 10 to the power minus 6 mho at an angle 90 degree. We have obtained series impedance per phase of the transmission line Z equals to 51 ohm at an angle 73.87 degree, and shunt admittance per phase Y equals to 395 into 10 to the power minus 6 mho at an angle 90 degree. Let us now calculate Y into Z. Using values we get 395 into 10 to the power minus 6 at an angle 90 degree into 51 at an angle 73.87 degree. That gives us 0.020145 at an angle 163.87 degree. This may be written in Cartesian form as minus 0.019352 plus J times 0.0056. Now we shall calculate 1 plus 1/4 of Y into Z, that is equal to 0.99 plus J times 0.0014. This may be written in polar form as 0.99 at an angle 0.081 degree. For pi equivalent circuit, A equals to D equals to 1 plus half of Y into Z, that is equal to 0.99 plus J times 0.0028. This may be written in polar form as 0.99 at an angle 0.162 degree. B equals to Z, that is equal to 51 ohm at an angle 73.87 degree, and C equals to Y into 1 plus 1/4 of Y into Z. Using values we get 395 into 10 to the power minus 6 at an angle 90 degree into 0.99 at an angle 0.081 degree. That gives us 391.05 into 10 to the power minus 6 mho at an angle 90.081 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 38,105 volts at an angle 0 degree. We have obtained receiving end current IR equals to 210 ampere at an angle minus 36.8699 degree, and generalized constants for pi equivalent circuit A equals to D equals to 0.99 at an angle 0.162 degree, B equals to 51 ohm at an angle 73.87 degree, and C equals to 391.05 into 10 to the power minus 6 mho at an angle 90.081 degree. Expression for sending end voltage per phase Vs equals to A times VR plus B times IR. Using values we get 0.99 at an angle 0.162 degree into 38,105 at an angle 0 degree plus 51 at an angle 73.87 degree into 210 at an angle minus 36.8699 degree. That gives us 46,277.185 plus J times 6,552.1 volt. This may be written in polar form as 46,738.72 volt at an angle 8.0586 degree. And expression for sending end current per phase Is equals to C times VR plus D times IR. Using values we get 391.05 into 10 to the power minus 6 at an angle 90.081 degree into 38,105 at an angle 0 degree plus 0.99 at an angle 0.162 degree into 210 at an angle minus 36.8699 degree. That gives us 166.651 minus J times 109.368 ampere. This may be written in polar form as 199.33 ampere at an angle minus 33.2757 degree. On no load, receiving end current IR equals to 0. Therefore, receiving end voltage per phase on no load VRO equals to Vs divided by A. Using values we get 46,738.72 at an angle 8.0586 degree divided by 0.99 at an angle 0.162 degree. That gives us 47,210.828 volt at an angle 7.8966 degree. Now we shall compute voltage regulation, that is equal to VRO minus VR divided by VR. Using values we get 47,210.828 minus 38,105 divided by 38,105. That gives us 0.239 per unit or 23.9%. We have obtained sending end voltage per phase Vs equals to Vs at an angle delta equals to 46,738.72 volt at an angle 8.0586 degree, and sending end current per phase Is equals to Is at an angle minus phi 1 equals to 199.33 ampere at an angle minus 33.2757 degree. For star connected system, sending end current per phase equals to sending end line current. and line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 46,738.72, which is approximately equal to 80.954 into 10 to the power 3 volts or 80.954 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 8.0586 degree plus 33.2757 degree, that gives us 41.3343 degree. Now we shall calculate sending end power factor. Cos phi s equals to cos of 41.3343 degree, that gives us 0.751 lagging. Now we shall determine sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 46,738.72 into 199.33 into 0.751, which is approximately equal to 20.99 into 10 to the power 6 watts or 20.99 megawatt. Now we shall determine efficiency of transmission. Eta T equals to PL divided by PS. We have computed power delivered to the load PL equals to 19.2 megawatt. Therefore, eta T equals to 19.2 divided by 20.99, which is equal to 0.9147 per unit or 91.47%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learnt how to determine ABCD constants of a three-phase medium length transmission line based on its nominal pi equivalent circuit. We have also learnt how to compute percentage voltage regulation and efficiency of transmission of this line using those constants. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.